Okay, so we are ready to prove the finite R transform theorem. Again, we are going to still need to prove two small lemmas and then, or mid-sized lemmas, and then move to the proof itself. So let's get to it. Right, so this is the plan. We did a pinching lemma, we just proved lemma A and little lemma on the way. And now we're going to move lemma B, C, state D, and prove the theorem. Okay, so lemma B actually handles the case where one of the polynomials is x minus lambda to the d. So let's say the second polynomial. So it has this one root, and P is any real-rooted polynomial with a positive leading coefficient of degree exactly d. So what we want to prove in this case is this thing. It's the same statement that we had before, but for the specific case of Q, which is x minus lambda to the d. And actually, that's quite straightforward. So let's say that A is a normal matrix whose eigenvalues or characteristic polynomial exactly captures P of x. Right? You were given some polynomial of degree d. You can always find a d by d matrix A, which is normal, namely, well, you have two definitions for normal, right? Either they're equivalent, either they're commute with the conjugate, its own conjugate, or it has a orthonormal basis of eigenvectors, at least for finite dimensional operators. So I'm considering the second one. So I'm just, choosing some, or for maybe just, some orthonormal basis of eigenvectors and just scale or reflect each of them according to the corresponding root of P. So you can always find such a matrix that kind of realizes P. And let's take B to be lambda I. Lambda I because you see Q has, that's the matrix that kind of corresponds to Q because Q is the characteristic polynomial of that matrix. A and B are both D by D matrices. Then what can we say about the additive convolution of P and Q? Well, by definition, it's this expected characteristic polynomial according to the Haar measure. But in our case, B is just lambda I. So Q and Q conjugate collapses to get I, and so you just get A plus lambda I. In particular, there is no dependence on Q anymore, so the expectation goes away. And you are really left with essentially the characteristic polynomial shifted by lambda. So it's exactly P of x minus lambda, right? Because this thing is this determinant. And so just coupling x and minus lambda together, you see that you get the characteristic polynomial, which we denoted by P of A, but evaluated lambda, shifted lambda by lambda. Okay, so that's we just understood this part. It's this thing. So this means that if you apply the U alpha operator to this polynomial at x plus lambda, it's like applying the U alpha operator at P at x, right? Because U alpha is just what it does is just it has P and is subtracted alpha times P prime, and both P and P prime are the relation between P and the convolution is shift by lambda, so that translates to the U alpha operator as well. In particular, the max root of this polynomial is attained exactly where the max root of this polynomial is attained plus lambda. Good. So we figured out what this is. It's the max root of this plus lambda. So it's this thing plus lambda. So we just have to figure out, what this is. So what is U alpha of Q? And it's a very simple polynomial, it's just a distinct root polynomial like that. So U alpha of x minus lambda to the d, again, just x minus lambda to the d minus alpha times the derivative. You can pull out x minus lambda, the minus 1, and you'll be left with this. And because alpha and d are non-negative, this is the max root. So lambda plus alpha d is the max root. And that proves the star because this is lambda plus alpha d, which gets cancelled with this. And we just show that this is this plus lambda. So everything It's great. So that's lemma B. It's a simple lemma. Lemma C is even simpler. It has nothing to do with additive convolution or anything. It just tells you that if you take a polynomial in PD and the degree is at least 3, okay, that's important. And you happen to know that the derivative of P has just one distinct root, so it may have the same root repeated, but only one root, then so does P. Okay. So P also has to have one distinct root. And the reason is, you start with this P and you compute its derivative and you get one root. And so P has degree D, so this means that the derivative is of this form. It's some number A times x minus lambda to the D minus 1, where lambda is that one root that we assume that the derivative has. So what does it mean? It means that the original polynomial is this thing, right? You integrate and add a constant. And so because we assume that D is at least, okay. So if C is 0, we are done, right? Because if P of X is this thing without C, then yes, indeed, this is the case that P has one distinct root. So, but if C is not 0, and as D is larger than 3, you see a solution to that equation will involve like D roots of unity, right? It's you move C to the other side, multiply by D, and divide by A, and then you take all the diff roots. So it will involve the diff roots of unities. And since D is at least 3, at least one of them, even actually 2 of them, would be complex valued in contradiction to the polynomial being real rooted. Okay, so to recap, this lemma tells us that if you have a polynomial of degree at least 3, which is real rooted and a positive leading coefficient, doesn't really matter, then if you know that the derivative has one distinct root, then so does P. It's a property of real rooted polynomials. Good. So that's the second lemma. The third lemma, which actually is it's more significant, and we'll have to defer the proof for a later video. It will be a corollary of something that we anyhow want to do. It says the following. It kind of connects the diff convolution with the D minus forced convolution as follows. So say you have a degree D or at most D polynomial P, but Q is of degree at most D minus 1. So it's another polynomial of a lower degree at most D minus 1. Then there is a relation between the D additive convolution of these two polynomials and the D minus 1 additive convolution of Q and the derivative of P. Right? The derivative of P has degree at most D minus 1, so both of these polynomials have degree at most D minus 1, so it's valid. And it turns out that the relation is quite simple. So the D additive convolution of the two polynomials is the D minus 1 additive convolution. Q remains the same, but you just have to replace P with its derivative, normalized by little d. Okay, so that's something that I'm not sure it's easy to see from the actual definition of the way we have it so now, like the expected Haar polynomial, expected characteristic with respect to the Haar measure, sorry. But there is an explicit formula for the additive convolution, which you will see, and from there that's kind of follows almost immediately. Okay, so lemma D is you should trust me on that for now. Okay, so with that, we're actually with lemma A, B, C, and D, we are ready to prove the finite R transform theorem. And just recall, our goal is to prove this thing. Is to prove that for every alpha, this inequality holds, and strict equality if and only if polynomials don't have distinct roots. Have distinct roots. So indeed, lemma B proves the theorem if either P or Q is of the form x minus lambda to the D. Like in a sense, it's kind of an induction basis, but not on the degree, on the number of roots. It's not induction basis, but it's a simpler case. So we can assume that P and Q don't have this property. So both P and Q have, each of them has at least two distinct roots. Because in the first, lemma B handles the case where in which one of them has one repeated root only. And the proof is going to be by induction on D, which is the maximum degree between P and Q. And again, as I said, we're going to prove the stronger assertion that we need to prove, which we have strict inequality in this case, right? Because in the first case, lemma B tells us handles that case. So the base case, degree 1 is actually already handled by lemma B, because degree 1, you cannot have two distinct roots. So you can either consider this as the base case, or you can, and actually you should do the D equals 2 base case. So let's say that we did the degree 2 also as well, because we need it. So let's assume that D is at least 3 actually, and we did degree 2, even though we didn't. Now, okay, for a fixed Q, let's define phi of P, like of any P, not just the P that we have, to be this thing this expression which we really want to show is non-negative or strictly positive in the case of distinct roots. Right, so it's very similar to what happened in lemma A, but now we have this Q also, which is part of the definition of phi. Okay, so phi of P is the max root of U alpha P plus the max root of U alpha Q, minus that, and indeed, if this is indeed strictly larger or equal than 0 or strictly larger than 0, depending on the case, then you get the bound that you want, because you can move this to the other side. Okay, so as in the proof of lemma A, it's actually very similar. We are going to assume by contradiction that that's not the case. Namely, there exists a P with at least two distinct roots for which phi of P it's always phi sub Q of P, but let's ignore that to save some notation. So phi of P is at most 0, and that some polynomial that we assume by contradiction exists. And as in the proof of lemma A, let's say all of its roots are in some interval minus R, bounded interval, a closed bounded interval. And let P0 be the minimizer of phi with respect to this set, right? All polynomials and PD, all of the roots are in minus R, like in the proof of lemma A. Right, because it would be more difficult to work with P because we know nothing about it, but for the fact that it's a contradicting assumption, P0 is a minimizer for phi, so you can have something to actually contradict. And here we use compactness as before. And as before, as in lemma A, we can also assume that P0 has at least two distinct roots. Again, if phi of P0 is strictly negative, then lemma B implies that. Because lemma B tells us that you cannot have a repeated root and have phi strictly smaller than 0. And if phi of P0 is larger or equal than 0, or actually I should say equal to 0, then we can take P0 to be P. Right? I mean, it should be equal, but anyhow. And P, we assume, has two distinct roots. So what do we know so we are going to apply the pinching lemma to P0 as in lemma A. And what do we know from the pinching lemma? So we know that you can write P0 as the sum, and you know that the roots of P tilde are interlaced between the roots of P, or I mean, that's true, but actually most of them are the same now. But anyhow, the roots are in the interval minus RR, which in particular implies that. Right? That's the thing we are going to contradict, because P tilde is one of the participants in this set in which P0 is a minimizer, or P0 is a minimizer of phi. And of course, we know that the max roots of the U operator apply to tilde, hat, and 0 is all the same. Of course, also U alpha is linear, and because U alpha is linear and the additive convolution is bilinear, we know that we have this equality. Right, and by lemma D, we know that, so that's the lemma that its proof is missing. We know how to relate this thing, right? P hat has degree D minus 1. So Q doesn't, but P has degree -1. So you can relate the DRT, the diff convolution, the additive convolution, with you can relate it to the D-1 additive convolution by taking the derivative. There was a factor of 1 over D, but we're looking at max roots. So this factor just goes out of the additive convolution and doesn't affect the max root at all. So by lemma D, we know this equality. And also we call that Q has at least two distinct roots. So by lemma C, which let me just remind you, it's this little lemma that told you that if you know a polynomial is such that its derivative has just one root, like distinct root, then it means that also the original polynomial has this property, assuming rootedness. So by lemma C, we know that dq also has at least two distinct roots, right? Because if dq doesn't have two distinct roots, then if it has a single root, then also q should have one, but it has two distinct roots. Actually, that's not exactly true, because in lemma C, that was under the assumption that the degree of q is at least 3, right? Because you need a third root of unity in order to get a complex value to root and contradict the assumption of real rootedness. So there is a slight gap here. That's why I said we should actually prove the way I see around it is that you just need to prove the base case for degree equals 2. And now we are in degree equals at least 3, and therefore you can apply the lemma C. Right, lemma C requires the degree to be at least 3, also in the proof, not just in the statement. So let's assume that just we already handled degree D equal 2, like by the way we did for lemma A. We proved the degree equal 2 separately. So let's assume the degree of D is at least 3, and therefore we can apply lemma C, and I will leave you to deal with the case that the degree of Q is at most 2. Okay, so but we do know now that by lemma C, because the degree is at least 3, that dq also has two distinct roots. Okay, so what do we know? So this is just repeated what I said before. Lemma D implies that the max root of U alpha of this convolution is the max root of this convolution. Here it's a D-1 instead of D, right? And use the derivative. Now the point here is that now both of these polynomials have degree at most D-1. Otherwise, I also couldn't have do that. And so you can apply induction, right? Because the induction was on the max degree. So now both polynomials have degree at most D-1, so you can induct, and just you get this inequality that you see here. Right, everything is with like the hats and the DQs where they should be. Here is a hat and here is a DQ. But now by the pinching lemma, U alpha of P hat and U alpha of P0 has the same max root. So I can replace this hat with a P0. And lemma A tells us what's the relation between the maximum root of U alpha DQ and the maximum root of U alpha Q. It says inequality, not strict inequality, but recall that there is a strict inequality in the moreover part of that lemma, exactly when Q is not of the form x minus lambda to the D. And we just said, using lemma C, that that's the case. So it has at least two distinct roots, which implies strict inequality here. And then this is the minus D alpha, but now this is the -1. So you get this. So anyhow, what this tells you is that you can replace P hat with P0, get strict inequality, remove the D to get the alpha Q. You remove the D, but you get a strict inequality, you get something. Minus alpha, which there's also the minus alpha, which joins to the minus D-1 alpha here to get minus D alpha. And this is exactly the expression for the max. So this is, so if you look at phi of P0, and since you know it's at most 0, this thing is bounded from above, not strictly, but by that thing. And because phi of P0 is precisely the difference between these two. So, you have only one strict inequality, but that's enough. What we just proved is that this thing is bounded by that strictly. Uh, okay, so with that in mind, let's also recall that right. So that's used the bilinearity of the additive convolution and the linearity of U alpha. That U alpha of the P0 version, see, P0 player is equal to that of the hat and the tildes. And by the little lemma, we know that now. Right? We know that the maximum root corresponding to the tilde is strictly larger than that corresponding to the zero player. Right? Why? Because we know that the maximum root of the P0, so we know that the zero player is at most the tilde, the maximum between the tilde and the hat, but we just showed here that the hat doesn't win the zero player, right? The max root of the thing with the hat is strictly smaller actually than the maximum root of the thing corresponding to zero. So the maximum, the fact that the maximum is at least it wins the zero means that the tilde is the one that's larger. So what I just said is this inequality. But from the moreover part of that little lemma, we know that there will be strict inequality as I kind of claim here, unless all of the three are equal. But not all three are equal because we just proved that the hat, again, I'm using it again, the hat and the zero polynomials are not equal. So anyhow, you get this strict inequality. It's very similar to lemma A. That's why I think I'm saying it quite fast. Okay, so kind of ignore that. I just expanded it here. So with this in mind, that's what we just proved. So let's look at phi of p tilde now, right? So phi of p tilde by definition is this thing. And we know that the first sum in here, the max root of u alpha p tilde is the max root of u alpha p0. That's the pinching lemma. And we just proved this inequality that the tilde player is larger than the zero player, but it's with a minus. So when you take this into account, you get strict inequality to the same expression as here, but only with p0s instead of p tildes, which is exactly phi of p0. And p tilde is one of the contenders on it's one of these elements here. All of its roots, it's in PD, and all of the roots are by the pinching lemma are between minus r and r. So it's one of the contenders, but we just showed that it's strictly smaller than the minimum. And that stands in a contradiction to the choice of P0 and to the existence of any polynomial P for which phi fails to be larger than 0. Good, so I know it's technical, but again, it is what it is, and that's the proof of the finite R transform. Right, it's very different than the proof of the R transform theorem, and it's a really interesting question to ask whether you can relate the two, get proofs that are similar, maybe understand in what sense these proofs may be similar, even though they don't look like they're similar, or maybe these are indeed two very distinct proofs. I don't know, I have more questions than answers. But going back to what I can say, so let's see what we did. So we just proved the FPT R theorem, the finite R theorem, which will be the main tool. It's like the most technical part that we have moving forward. We have two other parts, the quadrature and the interlacing. They are also very interesting and obviously non-trivials, but this was the most technical part, the R transform theorem. I still owe you lemma D. I said, I don't know why there is a like a green happy sign here. I still owe you lemma D, which will follow from the next unit, which will be a short unit about a formula for an explicit formula for the additive free convolution. It's a good to see the formula also because it gives you some more insight about what's really going on. I mean, right, the expected characteristic polynomial with respect to the Haar measure is an integral. It's a highly non-explicit way. It's explicit, but it's not something that you can actually easily compute. So it would be nice to have an explicit formula, and actually we have more than just a formula. We'll have different ways of viewing the additive convolution. So it's going to be insightful. In particular, going to imply lemma d. And with lemma d, we actually have the proof of the R theorem, finite R theorem completed. But for the fact that we always assume implicitly that the additive free convolution preserve relatedness, which is true, but we need to prove it. And that will be part of what we'll do when we'll do the interlacing step. Okay, so next up is a explicit formula for that. That will be essentially lecture 10. Or maybe I can also add the quadrature, and then we can do the interlacing and finally get the result of MSS about the existence of bipartite Ramanujan graphs or one-sided Ramanujan graphs as a corollary, essentially.